Hey everybody, this is the charge, voltage, and current module. I'm Michel Maharbiz.
And I'm Vivek Subramanian.
Let's get started.
In the module today, we're going to talk about various fundamental electrical parameters. And the first parameter to talk about is charge. Now, the unit of charge is a coulomb. And it's important to note that charge can be either positive or negative. So the unit of charge just tells us, if I talk about a certain number of coulombs of charge, that will generally be positive, but I can have both positive and negative values. Now, in terms of what provides charge in electronic systems, the fundamental quantity of charge that we talk about is the minimum charge that exists in nature, and that is the charge on a single electron or correspondingly on a single proton. Now, we typically denote this charge by a letter, and the letter we commonly use in engineering is the small e. Sometimes, by the way, I should point out, in some textbooks, you will see also a small q. But in either way, that would denote the charge on a single electron or a single proton. Now, you've probably heard that electrons are negatively charged and protons are positively charged. So an electron would therefore have a charge associated with a negative sign, and a proton would be positive. So E is 1.6 times 10 to the minus 19 coulombs. And so for an electron, the charge will be minus 1.6 times 10 to the minus 19 coulombs.
That's a pretty tiny number.
That is an extremely small number. It takes a huge number of electrons to give even 1 coulomb. And as we move forward and we start talking about real circuits, you'll see how much 1 coulomb actually is in terms of everyday things. Now, there are some important laws that we need to talk about, and one of the most important laws to talk about is the law of conservation of charge. The law of conservation of charge says the following. If we have a closed region, in other words, a region that is isolated from everything else and there's nothing interacting with it within that closed region, the net charge in that region can neither be created nor destroyed. Now, you'll notice I use the word net, and that's very important. Let's consider an example. Let's say I have a box, and it is a closed box, which has 5 electrons and 5 protons. The net charge in that box is 0, because the minus 5 and plus 5e cancel out. I could add 1 more electron and 1 more proton, or remove 1 more electron and 1 more proton, and all of that would still be consistent with the law of conservation of charge. The point is the net charge can neither be created nor destroyed. Now, the next step we're going to talk about then is once we've identified these fundamental units of charge, and in particular we've identified the idea of electrons being our fundamental quantity, the next thing we're going to talk about is actually current. And essentially what current involves is the motion of charge. So on the right hand side here we see 2 drawings. On the bottom I show a schematic representation of a circuit. It turns out to be a very simple circuit. It has a battery or a voltage source. It has a resistor. We'll talk about those later. And it has wires connecting them. We'll talk more about how schematics actually work later. But let's focus in for now on the wire. So I've taken this little drawing of a wire and I've expanded it out to show a physical representation of a cylindrical wire. And you know from your everyday experience that wires would typically be made of a metal such as copper. And when current flows through the wire, the way that is actually represented is we actually have electrons moving through the wire. So current then is motion of charge.
So this is a little confusing because I thought that information moved down a wire at the speed of light. But do these electrons actually move down the wire at the speed of light themselves?
No, they don't. In fact, in typical solids, including metals, electrons move much slower than the speed of light. So the information is propagating not because one electron goes all the way from the right all the way to the left, and then that's the electron you detect. The electrons are moving slower, but the aggregate motion of all of the electrons allows for much faster propagation.
Yep, sounds good. All right, let's talk a little bit about current. So current is comes from the fact that in a conductor, charges are relatively free to move about. And so what current's going to tell us is something about the movement of that charge within the conductor. Typical charge carriers can include electrons, as we've been discussing, and there's certainly in a typical metal, you can imagine any metal you're familiar with, copper or gold, aluminum, there are going to be many, many electrons that are so weakly bound to their the original atoms they came in that they essentially can freely move about that wire. You can also have ions. So ions are charged atoms or molecules that are ionized so that they carry a net positive or negative charge. You can think, for example, of sodium chloride, salt. When you put it into water, some small fraction of that Na and Cl is going to separate and ionize into a positive and negative charges that are somewhat free to move about in the water and respond to stimuli.
Hey, Michel, before you move on,
yeah.
I see you're talking about electrons and ions, and previously we said that what provides current in wires is the flow of electrons, but I see you have ions on there, and I know that lithium-ion batteries are getting a lot of attention these days. Does that have anything to do with electrons and ions?
Yeah, sure. So in the wires that the batteries are connected to, it's electrons that we're pushing around to do the work, right? So to power your laptop or to light a light bulb. But within the battery itself, it's actually the motion of the ions the separation of and the motion of those ions that gives us the ability to do work around the circuit. So definitely, ions and the behavior of ions is a key component in the behavior of batteries. There's another thing that another charge carrier that you'll come up against when you're particularly looking at semiconductors, and we call these holes. And for the moment, we won't get into much detail, but you can imagine a table packed as tight as possible with little white ping pong balls, and you remove a ping pong ball, leaving behind a gap, and then you sort of move another ping pong ball into that gap and so on, so that the gap itself appears to move around this sea of little ping pong balls. That lack of a ping pong ball is essentially a hole, and this occurs in semiconductors where there'll be relative to the lattice of the semiconductor, you'll see there'll be a gap in say an electron that's absent, and that gap itself can move around, and we call that a hole. It's fundamentally important in the operation of diodes and transistors and other solid-state semiconductor devices, and we'll touch upon that in the course a little bit. So the net point this slide is really that current is charge in motion. So if you get the concept of charge and you start to imagine or come up with models in your head as how that charge can move about, one of the descriptors of that charge in motion is what we call current. So let's look at some simple examples. So here on the left, we've got a single positive charge. We'll call it Q1, and it happens to be moving to the right. And so this will present us with a current I1, and we'll get a little more detail into how that works. But basically, this is a current to the right. And here, you think of a negative charge just below it, and it's moving to the left, okay? And we'll call that a current I2. The key here is that the net current basically the net current across some fictional cross-section, say these two things were moving in a wire, would be I1 plus I2.
Is the reason for that because one is positive and one is negative, and since they're therefore moving in opposite directions, the effect sort of the minuses, so to speak, cancel, and you end up getting a net summation? Yeah,
in fact, let's look at this example here. And this, I think, will answer your question and flesh out the first one. So in this case, I've got, again, the same positive charge moving to the right, but now I've got a negative charge, and it's also moving to the right. And you see in this case, and we'll go back to both of them, you see in this case, the net current is I1 minus this, essentially the magnitude, this I2 subtracted from it. So if you think about this, what's happening is if I had two positive charges moving to the right, I would sum the currents I1 plus I2, and that would give me the current to the right. If I had a positive, like I do on the left, charge moving to the right, and a negative charge moving to the left, these essentially cancel out, and I again get this I1 plus I2. And if you look at the second example on the right, basically because the negative charge is moving in the same direction as the positive charge, it effectively subtracts out a little bit of the current.
And when you said cancel out with respect to the left figure here, you meant cancel because the negative sign and the negative of the vector are canceling out.
That's exactly right. So let me summarize all this, I think, in a very straightforward way, which is now to be more formal. If you pick some surface, okay, so that surface could be the cross section of a wire. Take a wire and cut it down, essentially cut it down the middle, and you look at all of the charge that's crossing through that cross section in some little bit of unit time. So the net charge in some unit time divided by that unit time gives us the current. Okay? So think about this for a second before we even look at the units. Let's go back to our example. If I've got one positive charge and two negative charges crossing some boundary, the total charge or the net charge is really -1. Does that make sense?
Yep.
And they're both moving to the right, and so that explains this right example right here where I subtracted the two. If I have the same surface and I've got a positive charge going through it to the right and I've got a negative charge going the opposite direction, not only are these opposite sign charges, but their vectors of the direction are opposite sign, and so again I get these canceling out and I get I1 plus I2. And so the units of the current are quite naturally, just by this explanation and looking at the expression, are coulombs per second, because we've got charge in the numerator and it's in coulombs, and we've got time in the denominator, it's in seconds. And that's given the unit name of an ampere after André-Marie Ampere. We'll come back to this other definition later. If you think about it for a second, it's also very natural to express this expression in differential form here, and that's just to say that any arbitrary current, whether it's time variable or not, can be expressed as the derivative of the charge q as a function of time, dq dt.
Okay, having now introduced the idea of current, let's start going into some details on the current. And I'm going to use a specific example to show you how magnitude and sign of current matter. Let's consider a situation where we have some circuit, and right now we're not going to worry about what's in the circuit. We'll just draw it as a box. And I'll say that the circuit has two ports to it. And the ports have a wire between them such that current flows through the wire. And in this example, I have 5 amps of current, and the 5 amps of current are flowing downwards. In other words, from the top port, out through the wire, down to the bottom port. That's my first example. In my second example, I have the same circuit, but I've changed it, and now I've defined the current as being -5 amps, but it's going from the bottom port to the top port. So, Michel, here's a question for you. What can you tell me about the relationship between those two currents?
Are they the same current?
They are, in fact, the same current. And the reason they're the same is this is +5 amps moving downwards. This is -5 amps moving upwards. Because this is minus, but going in the opposite direction, the negatives effectively cancel themselves out, and we end up getting 5 amps going downwards in either case. So these are therefore equal.
So are you saying that if I've got a circuit I'm solving for when I get a homework problem, and I happen to draw the current that I'm solving for on this branch up here downward, I'm going to solve for a current, I draw an arrow, and I go about my math, and my friend Sue drew the same arrow on her homework problem on the same branch pointing up, I should expect to get 5, and she should expect to get -5, but effectively we've solved the same problem.
That's exactly correct.
All right. So I want to take a little break here from that to give you help you start developing an intuitive notion of how charge actually moves. So first of all, in any real material that isn't at zero Kelvin, which is basically everything, there's always a little bit of thermal velocity. And so by that I mean, again, let's think about your favorite metal and the fact that there's all of these weakly bound electrons that are moving about and are free to sort of be biased to move in that wire. They're all jiggling a little bit. There's always a little bit of thermal motion, and that's due to the fact that everything's at a finite temperature and has a finite amount of sort of random vibration, random energy. So here you can imagine I'm taking a snapshot of a simple 2D version of this, and I'm plotting all the velocity vectors for every electron. You can see they're all over the place. Some are going left, some are going to the top right, and so on. But the point is, if I'm not applying some sort of external stimulus to get them to move in a uniform direction, their total velocity is going to add up to 0. They're all just all over the place, but on average, they're not going anywhere.
So, Michel, if I understand you correctly, what you're saying is that the electrons can be moving, but because the net velocity is 0, would I be right to say then the net current is 0?
That's right. These things are essentially not producing any net current. They're all sort of canceling each other out if we sum it over a large enough ensemble. Now, to get exactly to your point, here's a counterexample. So here's an example, and you can't quite see it until you kind of defocus your eyes a little bit maybe. But in this case, the vectors are a little bit pointing more to the right than anywhere else. They still are randomly wiggling, so that component of thermal velocity is still there. They're all still jiggling because that's a property of the temperature that they're at. But I've somehow applied, say, an electric field or something that's going to bias them so that there's a net motion to the right. So they're all still jiggling, but the total addition of all of the x and y components, the y's will cancel out, and there'll be a little bit of an x component left behind that points to the right. Does that make sense?
That does.
All right. So, Vivek?
So far, when we've been talking about current, we've essentially been taking it as some sort of fixed number. We've said we had 5 amps of current flowing in the example that we looked at earlier. And in fact, there are many systems that we deal with on a regular basis where current is a fixed number. The classic example is if you take a battery and you use it to drive a fixed load. For example, I use it to drive a light bulb. The current out of that battery will be pretty fixed until the battery discharges quite a bit, and then it'll drop off. By the way, Michel, I should point out, that's why light bulbs get dimmer as batteries discharge, because ultimately the current drops off.
Got it.
But that's not the only type of current we have. That type of current is called the DC case, where the current is not varying with time, and DC stands for direct current. All of you are familiar with the fact that our electricity is delivered in what we call AC, and that's alternating current, and specifically, that's current that the current varies in a sinusoidal way. In other words, if we look at the current as a function of time, it has a shape of a sinusoid. Sometimes it's positive, sometimes it's negative, hence the term alternating current. There are other types, and that's a clear example of something that's varying as a function of time. There are other examples of things that vary as a function of time. For example, we can have decaying current, where the current starts at a certain value, and then it slowly drops off. We can have rising current, where the current starts at a certain value and then goes higher. And we can actually do combinations of these. For example, something that appears to be a combination of an AC current and a decaying current would be a damped oscillatory current, where it's oscillating downwards. You can see it looks sinusoidal, sort of, but it also is decaying at the same time. And so we see a situation of damped oscillations.
So I'm looking at this, and E, the damped oscillatory trace, looks kind of like I took maybe something that's decaying and added on a smaller sinusoidal component. Is that a good way to think about it? Or?
That is, and you're introducing an important idea called superposition, which we will get to later.
Oh, I'm jumping ahead. All right, won't do that. Okay, and so now it's a great point to turn to a neat little demo that Vivek has that gets to sort of the direction of current, positive and minus, to sort of illustrate that point.
All right, so let's get started with a demo to show how current and a sign and magnitude are related, and specifically the equivalence between direction and sign as far as currents are concerned. To demonstrate that, I'm going to use this. This is a light-emitting diode. Now, a light-emitting diode, also commonly called an LED, is a device that will light up when current flows through it, but only in one direction. Specifically, here's what I'm going to do. I'm going to take my light-emitting diode, and I've got a power supply set up over here, and over on this side I have a multimeter which is set to measure the current flowing through the light-emitting diode. So I'm going to take the light-emitting diode, and one end of the light-emitting diode I've connected to a resistor, and that's just to make sure that I get the right current through it. If you put too much current through a light-emitting diode, it can burn up. So I'm going to connect the red to the resistor end, and I'm going to connect the black, which is the negative, to the other end, and you see that it lights up. So again, disconnect, it's off, connect, it lights up. And then if you look at the current, you see that it's 12 milliamps, or about 13 milliamps flowing through this device. Now, here's what I'm going to do with this light-emitting diode. I am going to flip it such that we're going to have current that is negative. So I switch over to that side. I connect this again. Haven't moved the red connection. The red is still on the resistor. The black is on the other side, and it doesn't light up. Now watch when I reverse it. I'll connect the red on the other end, and I connect the black to the resistor, and it lights up. So you see that I've now got minus 12 milliamps of current, but my LED lit up. And the reason is minus 12 milliamps going left to right is the same as 12 milliamps going right to left. So you see how the LED worked.